All right, thank you very much for the opportunity to give these talks here and this very nice program. So, okay. That's okay. Okay, that's how. Oh, okay. Sign so we can find it. Yeah, the other the same thing. So, of course, since this is just some lecture or classes, feel free to ask questions anytime if something is not clear or just you have a question. And then we talk about certain topics. Is kind of on the interface of harmonic analysis and analytic number theory. And one can go two different ways, either to emphasize the number theory part or the harmonic analysis part. I decided to emphasize the later. So I won't go into more general operators coming from more general lattice points and more general surfaces determined by higher degree polynomial. I will mostly consider just lattice points on spheres and mention like how these type of things generalizes to other quadratic forms, sometimes even higher degree forms. So what I will talk about today is maybe a discrete analog of Stein's spherical maximal operator. And so quite some time ago we obtained a discrete analog with Eli Stein and Steve Wenger of the boundedness of this operator in the discrete settings, in the settings of the underlying space being the integer lattice. And the proof was relatively complicated. Today I want to present a simpler and newer proof just of the two boundedness, and it uses a certain property of the Fourier transform, the lattice points on spheres, which can be used to prove other results, which I will talk about later. So let's just give the title, just discrete. And let me know if my handwriting is not good enough or small, or it's it cannot be seen. And let me just invoke, let's say, the famous theorem of Stein and Bourgain, which is in the Euclidean setting. So this was proved by Eli Stein in the mid-70s in dimensions at least 3, and by Bourgain later, I think in the late 80s, mid to late 80s, for V equal 2, which is technically much harder. So the theorem says that let B is at least 2, and P is bigger than B over B minus 1, and let's say you have a function in LP, RP. Now, we define spherical averages. So define, let's call it average A, lambda f of x, to be equal to the convolution of f with sigma lambda, which is the normalized surface area measure. So the total measure of the sphere is 1. So let's say sigma lambda is the measure of the sphere of radius lambda is lambda to the d minus 1. So that's a normalizing factor coming to surface area measure. So these are, of course, lambda is a positive number. So this is basically just taking a point x, taking a sphere of radius lambda and averaging f on this sphere. That's the convolution of x. The average of the sphere translated to the point x. So a lambda of f of x is the average of f on this sphere. And now spherical maximums, then you take a soup over all lambda. So let's define A star and X. This is supreme over positive lambdas, A lambda at X. So it's very okay. So this is the spherical maximal operator applied to F. And then the theorem says that this is boundary of the P norm bounded by a constant times that P norm again, as long as P is bigger than the order complex. So that is now notice when B equal 2, then the range is P bigger than 2, and that makes it much harder. You can't use directly in L2 theory, so to speak. And it is sharp, and you can check little homework, the sharpness very quickly. This range is sharp. Theorem is not true when P is less than equal to over B minus 1. And the example is very, very simple. Let's take function f, let's say f naught of x to be equal, basically the indicator function, the unit pole. That shows the sharpness simply because a hint that this is where your function support. You take an x, let's say which is minus at least 2, and then you look at all the averages from x, and the ones which hit this function, now those in lambda is say equal x, and then the integral itself is about 1, but the normalizing factor takes it to be x to the minus d minus 1, so you get a star at 0. You get an equal x to the minus d minus 1. So if you integrate the d's power of that, and it would be only integrable if d minus 1 factor is bigger than d. And that shows the sharpness. Okay, so now so the discrete analog we were thinking of this theorem is basically try to prove the same thing that the other lines.
Just one question.
Yeah.
But in theory, just because it's not integrable, it's still possible some kind of weak inequality, right?
Yeah.
Or not?
Well, but I think that the range is still the same.
Yeah.
Except maybe at the end, which I don't quite remember.
Okay.
But other than that, the range is the same. So a discrete analog of this is very similar, but here, what is S lambda? So first of all, so let's define a discrete sphere, which is nothing else than a set of lattice points on the sphere. So let's say those are x in ZB. So the coordinates, each is an integer, such that, let's say, x squared equal lambda squared. And of course, this is only non-empty, when lambda squared is an integer. So lambda is the square root of an integer. Now, that could be empty. So what does it mean? How many points you have here? Well, so that means that x1 squared plus xd squared equal lambda squared, which is an integer. So there is only a lattice point on this sphere. If lambda squared can be written as sum of these squares. And that is kind of a problem in number theory, which has been studied for a long time, starting with the work of Jacobi and then Hardy and Littlewood and so on. So this could vary. The number of lattice points on spheres could vary very widely, especially in low dimensions. So, but in dimension at least 5, it's kind of relatively becomes stabilized. So that is a result of going back to Hardy Littlewood that we just mentioned. two things. So when d is bigger than 5, there exist two constants, two positive constants, such that CD, lambda to the d minus 2, that's an equal as lambda, that's an equal capital CD. At least some lambda is bigger than some fixed constant. For d equals 4, that's more interesting. That's very well known. There is an exact formula. Goes back to Jacobi, and that raises a question which I will ask, although it doesn't seem to be an easy question. For d equals 4, then S lambda is 8 times the sum of the following divisors of lambda squared. So let's say if I already use this, I need another letter, let's say m divides lambda squared, which themselves not divisible by 4. Remember here it's really lambda squared is the integer. I just want to use the same setup times n. And this could be very small if lambda is the power of 2. It's just 8 times 1 plus 2, because these are the only divisors of 2 to the k which are not divisible by 4 equals 24. So there are certain spheres in the 4-dimensional integer lattice, which has only 24 trivial lattice space. Anyway, I just want to make this remark. So, and in this case, let sigma lambda be the normalized count on the set of lattice points. So it would be this, the indicator function of S lambda in ZD, normalized, as long as it's not empty. So there are at least, so you don't divide by 0. Okay, and then define the same averages, but now you average not on the sphere, but just on the lattice points on the scale. And then we had the following theorem, which I would like to talk about more in more detail, and that is a joint result with Eli Stein and Steve Wenger, going back to mid-2000s, and basically it says the following: if d bigger than or equal than 5, and p is bigger than d over d minus 2, then the maximal function on little LP, LP z to the d, applied to f, is bounded by constant times the LP f, where A star is defined the same way. So A star f of x is the supremum for all those lambdas where this as lambda is non-empty, but for d bigger than or equal 5, this is all lambda where lambda square is integer bigger than constant f star sigma.
I mean, it's always non-empty, right? Because of the dimension. These get to equal to 5, then it's always non-empty, at least for lambda.
Yeah, for lambda bigger than a constant. Yeah. In fact, yeah, you can calculate that constant, it's very small.
And in case of d equal to 4, then
d equal to 4, that's not empty, actually, by that formula, because that's an explicit formula, which implies that for d bigger than it's always non-empty as well, because it's a higher dimensional space, you can just take one coordinate 0. Of course, lambda squared has to be an integer here, so that's implicitly understood. Now, that thing, and the sharpness follows from the same counter example, same example, but here you can take to be the indicator function of 0. So sharpness, and In this setting, both conditions are sharp. So both b bigger than equal 5 and b bigger than b over b minus 2, both sharp, big and to be just solidic the function supported on one point. That's very trivial example. Or maybe it's let's not confuse with the distribution. And the reason is that instead of here, you would have x to the minus b minus 2 because the normalizing factor is number of lattice points on the sphere. So p times b minus 2 has to be bigger than b bigger than b over b minus 2. Now, of course, no, the only problem, this is only sharp because of these bad radii. Because then the maximum function is bigger than a constant, and lambda is when the length of x to the power of 2. So if you exclude those, then comes the question instead, like a 4-dimensional theorem. For example, let's just take a soup over all lambdas, the lambda square is an odd number, not divisible by 2. And then the range on p is bigger than 2, so that would be a discrete unknown games theorem. So that's like a question, but nobody could prove that. Later, I will tell you a little bit more reasonable question. Also, even if lambda is odd, this can still vary. Make sure that there's the number of lambda, because the sum of divisors are not very regular in general, even for odd numbers. Some odd numbers have a lot of divisors, some have very few. So it varies to some function lambda times something, which could be something as big as log of lambda, something like a log of lambda. Anyway, there is one can ask here a question which I think is reasonable, and it may not be explored, which I will mention. But let me start explaining the idea of first a partial result of an approach which we used in the discrete case, but explaining first in the continuous case. Okay, so let me try to prove it. A part of sinusoidal maximum just in L2 is just a dyadic function. Okay, and with a different approach. So let me okay. Okay, so to make this neat, I think I should push this up like this. Yes, this way. I don't want to break it. This and that. And I can call it a theorem, but hopefully, you will see the proof would be relatively simple of that. That's a baby version of theorem 1.1. Okay, so let's define and lambda is some positive number, and let's define the restricted maximum operator when you take the averages, but only in this range between lambda and 2 times lambda. So sometimes people say this is the maximum on one scale, on scale lambda, because the radii is between capital lambda and 2 times capital, not on all R. So then one has that a lambda star FL2, this would be just an L2 result, is bounded by a constant L2. And this constant is either uniformly in lambda. Okay, so let me sketch. proof of this result. So I will play with that small parameter. I will think of lambda to be somewhat large, but it doesn't really matter. In the discrete case, it would be. So let me introduce this epsilon, 1⁻². And let me be a little bit formal and think of the sphere as the delta function of, so then, basically, and you can make this precise, and in the discrete case, I will be precise, but you let it not be precise. Let me just say that sigma lambda x, the normalized surface area measure, thinking as a distribution, can be written formally the following way. It is the delta function of x squared equal lambda squared, because it's concentrated, this distribution, when x equal lambda. And for the reason that I can introduce the Fourier transform, I artificially embed the factor times e to the minus 2 pi epsilon x squared minus lambda squared. And this will do nothing because when x equal lambda, this is 1. But it would help us, so I can take the Fourier transform of a certain function. And depending on how you understand the delta function, I mean, the normalization is not in here, so that means I put this in here. Now, if you really think of how scaling works in this setting, actually, it works out this way. And now I use the inverse Fourier transform to expand the Dirac delta. And if you work this out, you can make this precise. First time again. And then now I just formally expand. And this is true if you work out carefully against the distributions, as if you integrate both sides against some test function, and then you can really use the inverse Fourier transform and it works out. Now, what's the point here? Well, so this everything is positive here, and lambda is between capital lambda and 2 times capital lambda. So up to a constant, you can estimate it this way. This term is just a constant because epsilon is 1 over lambda to the -2, so that kind of goes away. And here, what we do, we separate this term. And then what is left is some kind of a Gaussian type function. So what is left is e to the 2 pi I. And then you would have, there is an IT, there is an epsilon. And let me put it this way, e plus I epsilon squared, or maybe I can put it this way, epsilon minus IT x squared dt. So you might ask, why is this good? Well, let's see. The point here is that this in absolute value is uniformly 1, and that will give us a majorization. So now, what are we looking at? We're looking at these averages, and we want to, and actually looking at the soup of these. Lambda is about capital lambda. And now, how can we estimate this? Well, this is some kind of Gaussian. So what we see is that sigma lambda is an integral of this Gaussian with some oscillatory thing. Now, how can we estimate this uniformly? Well, this would be less than equal than a constant times lambda to the minus d minus 2. So now, for every lambda I want the uniform estimate, I can, when I convolve, I can put the convolution in here. And then I can just use the triangle inequality to pull the absolute value here, and that will give us a uniform estimate. So now the point is that this would be less than equal than the integral of f star, the epsilon gets absolute value dt. So this pointwise estimate is uniform, so it is true for the supreme. Okay, so once again, so if I want to take any lambda, I take the convolution, so the convolution comes in here. I take an absolute, I bring in absolute, and that terms, which depends on lambda, is gone. So we get a uniform estimate. So then we can use the Minkowski's inequality to estimate the L2 norm by the integral of the L2 norm of this term. So see. Organize. So this implies by Minkowski's integral inequality that if so, the left hand side is just this a lambda star, the maximum operator applied to f. L2 is less than equal to constant times 1 to the minus b minus 2, where the integral of f star dt epsilon L2 dt. But of course, the L2 of a convolution, if you go to the Fourier space, this is a multiplier. So in the Fourier space, this is f hat times the Fourier transform of this, which is bounded by the L2 norm of f times the L infinity norm of the Fourier transform. So this is further less than equal L infinity of the Fourier transform, and this would be a very unusual notation. I will use the continuous Fourier transform with a wiggle because I will use hat for the discrete Fourier transform or Fourier transform of functions on CD times the L2 norm. So all we need is to show that this is bounded by a constant. But of course, there's an explicit formula for the Fourier transform of a Gaussian, which we can use. Any questions so far? Okay.
I mean, it's kind of weird that the way you in the first equation you define the sigma lambda x is just a constant, isn't it? But then when you take the Fourier transform,
this is a distribution. So this is basically distribution of the surface.
Okay.
Yeah. So I could put of x, but it looks I mean, basically, if you integrate this against test function, and then or maybe it's even better to see if you look at kind of the integral of this function times t, what do you get? You get.
I mean, the Fourier transform.
So maybe it's better. Yeah, maybe it's better to put something like a modification here, which I put with the epsilon, but you can think of just some psi epsilon t, and you take the inverse Fourier transform. Then basically you get the Fourier transform of this function x squared minus t squared, as epsilon is going to 0. So this is something like epsilon t. You get phi hat something like 1 over epsilon phi hat x squared minus the squared over epsilon. And that's then going to 0. That's basically the which is the measure of the sphere. So it is just an exercise in Fourier analysis to get this representation. Now, in the discrete case, there won't be any problems because then it would be immediate. So you don't have to think about that you have such a representation, but you can kind of implement the idea of the discrete, starting idea of the discrete case in the continuous case, which is this. Yeah, basically, let you to work out that line if you try, and if not, I can need the details maybe next time. But this is kind of just an analogy of the argument of the discrete case and the continuous case. But now what is this? This is a Gaussian, and the Fourier transform of the Gaussian is explicit. So this the epsilon y at c. So this is a Gaussian function with a complex parameter, which is basically this minus 5 times 2z. So this you can think of from z. So that is standard Gaussian. The Fourier transform of that would be this to the minus d half times. So this would be epsilon minus it to the minus d half, and it would be e to the minus pi c squared over 2 epsilon minus it. And the real part of this is positive. So if you take an absolute value, you get an absolute value here. And that, since the real part of this is positive, in absolute value, this is less than equal than 1. So this is less than equal than the absolute value of this thing, which is just epsilon plus e to the minus d half. And if you integrate this function, and oops, have to be a little bit careful. So here is the first problem. D has to be at least 3. So that this integral works out. The main contribution of this integral is coming when t is less than equal epsilon. So this would be bounded by epsilon to the minus d half plus 1 to the minus d minus 2, which is basically less than equal than it is just 1 times 2. But d has to be at least 3. D equal to just doesn't work out because then just not integrable. So I put a little bit sloppy here. Already shows that the d equal 2 would be harder. By the way, there is no 2. That 2 theorem is not true when d equal 2. So this is the idea. Now, how does this work in the discrete case? And in that case, you don't have to worry about distributions at all. So again, this is less than equal 1. And so this whole absolute value is bounded by this. And if you integrate this in t and d half is bigger than 1, then the main contribution coming when t is less than equal epsilon. So that's a range of epsilon times epsilon to the minus d half. So the integral is bounded by epsilon to the minus d half plus 1. Okay. Or you can just change variables t to t over epsilon. You get the same. Okay, so let's go to the discrete case. And then the initial step is clean. Afterwards, though, you kind of implicitly has to use a method of number theory called the circle method, which was developed to count lattice points on spheres and more generally to count solutions of Diophantine equations, initially by Hardy, Littlewood, and Ramanujan. Okay, so now the discrete case. So so without lots of generality, we can use so what we have, without lots of generality, we can say that the sigma lambda is lambda to the minus b minus 2 times the indicator function of s lambda. So remember, s lambda is those lattice points which are on a sphere of radius lambda, so the length squared, the lambda squared. And why do I have this instead of 1 over s lambda? Because this majorizes 1 over s lambda up to a constant in at least dimension 5, so I don't have to, and I just want to estimate spherical averages. Okay. All right. So now we can start roughly the same way, but in this case, it is really clear that you can write this Because here x squared minus lambda squared is an integer, and you can just write it as the integral e to the 2 pi I x squared minus lambda squared t, where you integrate from 0 to 1. Instead of 0 to 1, I use the torus here, but that is just identified 0 to 1 dt. And I want to do the same trick, implement that extra decay factor where the minus 1 is there. And in the dyadic range, you can estimate this up to a constant. So you get basically the same thing, but here there is no problem because this integral is the very basic starting point of analytic numbers theory. If this is some kind of integer, and okay, maybe I write 0 to 1 first, e to the 2 pi I mt dt is 1 if n is 0 and 0 if n is not 0. And this is basically the starting point of many approaches in analytic numbers, which comes solutions to integer solutions to equations. So we would have the same thing as before, but now the integration is just 0 to 1. This thing is bounded, so we would have on the torus e to the minus 2 pi I lambda squared t, and then we would have the same Gaussian function as before, but now this is a function on the integer, on zt. Okay, so we have that, and then we would have the same estimate as before. So we would have now that a lambda star f, except the normalization factor is different. Little f2 norm is bounded by a constant minus e2 times the integral from 0 to 1 convolution of maybe so if the function is on ZD, it's still a multiplier. So the Fourier transform of the convolution is the product of the Fourier transform, which is bounded by the L2 little L2 norm of F times the infinity norm of the Fourier transform, but on ZD. So, but now this is the Fourier transform on ZD. When what this is, just to emphasize that now we are taking the Fourier transform on the this slide. Some x, and x is in C. So in order to get at least first a dyadic version, or in one scale of the Maximal theorem in the discrete case, we have to prove the same thing. So the proposition three, we need to prove the following estimate, that if you integrate from 0 to 1, the supreme, the infinity norm of the Fourier transform of the Gaussian, that is bounded by a constant times the normalizing factor, lambda to the minus b minus 2, And of course, the reason why we get, remember that set up to be. Once we have that, then as a corollary, we get an analog of the previous theorem, but in the discrete case. So a very special case of that theorem. We get that a number f 2 is bounded by a constant times C in 2 and this is an immediate corollary of this statement because we already estimated a number is with this one. Okay, so now, and one thing about this, none of these approaches uses what in the usual proof of time spherical maximum, an important thing is that the Fourier transform of the surface measure concentrated near zero. The approach I told you doesn't use that at all. So that's why this approach does not give you immediately the full maximal theorem, which is on all scale, and lambda is from 0 to infinity, just like on one scale. So one has to incorporate that kind of thing. Also in the discrete case, which would be something like that if you take the Fourier transform of the lattice points on spheres, they won't concentrate near 0, but they will concentrate near rational points. And one has to explicitly express this concentration to go from this theorem to prove a theorem on all scales, so lambda is from 1 to infinity. So that would be the next step, how to understand that kind of phenomenon. That is the phenomenon which you can use to prove other theorems. But anyway, just to have something which is not that technically complicated, let's start with this kind of special case of the L2 maximum. Okay, so the point okay, so let's try to estimate the discrete Fourier transform, and we will use Poisson summation because that's where you get the continuous Fourier transform of Gaussian, which you already know. All right, so let's start to prove our proposition, which is something which not quite see there. Well, oh yeah, so that's this. So now, so this Fourier transform is an exponential sum.
Sorry, what are we proving right now?
We are proving that this is bounded bundle.
Oh, which you mentioned somewhere, I think.
Yeah.
So in other words, we want to prove that the integral.
Proposition 1.3.
Yeah, exactly.
Yeah, proposition. Yeah, I lost it as well, so that I didn't. What I'm proving.
Yeah.
Shouldn't it be with a plus, proposition 1.3?
I'm sorry?
I mean, should it not be with lambda plus b minus 2? Because you want to cancel it, right? Is it even stronger?
Oh, yeah, sorry. Plus b minus 2, not minus b minus 2. Yeah, that's wrong. Yeah, the plus b minus 2.
What did you say?
Position 1.3 will be going to the plus.
Yeah, because the normalizing factor is not the minus d minus, then they should cancel.
Yeah, exactly what you
Sorry. If I make mistakes, I have to work hard physically. Okay. All right. So now these exponential sums over integers have a certain property. So maybe I write it down. My explicitly what is this GT? So sum over all x in ZD. And maybe just to emphasize that this is a exponentially decreasing function. So e to the minus 2 pi epsilon minus I t absolute value of x squared, e to the minus 2 pi x c. Now imagine when c is 0, then you have something like this type of sum. So now, just heuristically, so you have a decaying term e to the minus epsilon x squared, which kind of restricts the absolute value of x to like 1 over epsilon, which is about lambda. So we can think of x being less than lambda, and imagine what would happen if t would be a rational number. T would be a over q. Then since this is an integer, this would be, so if you would have an a of e to the 2 pi I a over qx squared, that would be periodic mod q. So roughly speaking, the cancellation you get in this case, that is rational, is then you take something like e to the 2 pi I a over qx squared, when x going through all the residue classes mod q, which is a standard Gaussian sum, which is a square root cancellation, you gain a factor of something like q to the minus d half. The larger the q, you more cancellation you gain. So this exponential sum is kind of concentrated large on points where t is close to rational. And this is the original idea of Hardy and Ramanujan. So for that, we will decompose the unit interval into neighborhoods of rational. This is called the Fairy dissection at a certain level. And on each little interval, we get a different estimate and we will sum those up. So what we will do, what is called the Fairy dissection at level lambda. So let's define f lambda to be the set of rational points a over q, where q is up to lambda. This is our scale, and a is relative prime to q. So that's a bunch of rational points. Now, according to that, we divide 0, 1 actually the torus, so 0 identified with 1, into intervals. Around each point, the interval, such that those points are the closest. So basically the mean dividing points. So then for given lambda, then its corresponding interval I, A, and Q would be the set of p's, where p minus a over q, p is closest to a over q, and all these rational points, so that's equal to the minimum of p minus r, then r is lambda. So to each rational point, there exists its own interval. The set of points which are closest to that particular points of them. So that maybe it's not necessarily symmetric. So we need to exercise very elementary, basically just what they sometimes call Dirichlet's principle of the pigeons, or how they say it, the pigeonhole principle.
Pigeonhole principle.
Yeah. Basically tells you then actually how small this can be. Basically, to every t there exists an a and q, so that t minus a over 2 is less than 1 over lambda q, because what you do, you look at qt minus a, the closest a, so you look at the fractional part of qt, and if q is going from 1 to lambda, then there should be this should be smaller for at least 1 to than 1 over n. So that's basically what you will have, that if you define J with Q, the set of T's where T minus A over Q less than equal to 1 over lambda Q, then basically it's very easy to see that this I AQ contains is contained in J AQ, and also easy to see if you shrink it by half, then it's contained in I A and Q. So roughly speaking, you can think of the length of this interval as about 1 over lambda Q. Okay, so that's visual homework to the result. Okay. So that is how much we need to know. And now a little calculation. Let's say you are in one fixed interval. So let T be A over Q plus tau, which is in one of these intervals. So we will use that and tau is less than equal to 1 over lambda. That's the only fact we will use at this point. Okay, and now let's do how we can estimate the size of this exponential sum when you are, when t is in one of these intervals. And as I said, the point of this is that for each interval, you get an estimate which will depend on Q. So you will have different estimates in different intervals. Otherwise, the estimate would be similar to what we got in the continuous case. But the calculation is a little bit more involved. So let's start. That is the definition. And here, if you write P as A over Q plus tau, and you look at A over QX squared, let's separate that term. Because that term will depend just on X mod Q. And then for the rest of the function is the same. So we would have just instead of T, we would have tau. And why am I doing that? Because this term only depends on X mod Q, so I will write X as Qy plus S, where S is in Z over QZ to the D, and Y is in Z to the D, so decompose X mod Q, and then this term will depend just on S. And then the rest is a sum in Y, and Y is in ZD. And then I would have this B tau X, I have Qy plus S, e to the minus 2 pi I, Qy plus S C. And for this part, I want to use Poisson summation. So this is some function evaluated at y. So some function evaluated at y. And then you take the sum of gy, which is the same as the sum of its continuous Fourier transform at y. Okay, so Poisson summation. And then there is a little, and if you are better in understanding the Fourier transform of a dilated and how this is called, not modified, but modulated function, but it's just standard, then you can calculate the Fourier transform. This is going to be just the Fourier transform G tau x, and if you do the calculation, what do you get? And what do you get? I have to cheat a little bit because it's always very easy to miss. Certainly, this part gives you a translation by C, and this part gives you, you divide by Q. So what you get is the following. If you apply some summation here, so first of all, from this change of value, you get the fact. Oh, by the way, I forgot one thing here, which would have been very useful. Notice that everything is additive. X squared is the sum of the square of the x1 squared plus x this, and x plus c is x1. So this is the product here. So basically, product of functions of one variable, and the Fourier transform would be the product of the Fourier transform of one variable. So we can think of here as one variable functions, if you want to. So, and that helps a little bit to think of this decomposition. But anyway, I wrote it in d dimension. So then I would have a 1 over q to the d. Then I would have a sum of s mod q over the residue classes in D. I would have this term. But I also will have, because of the shift, I would also have, when I evaluate, so I will use something sum of g of 1 equals sum of g continuous Fourier transform at L, where L is in ZD. So this is Poisson summation. So I would have this term, and then here I would have a sum in L in ZB from Poisson summation of basically the Fourier transform this function times e to the 2 pi I xc. So I would have the Fourier transform, the continuous Fourier transform of this function, which we know at L over Q because of the multiplication, and then the shift because of this term, and then because of this term, we would have an extra module. This goes into the modulation e to the minus 3 pi I as the L over Q. Okay, that's what we get. If we just do basically Poisson summation, basically you have this G function is essentially this times the modulation at 2y plus s. So for the change of variables. Okay, so let me rewrite this, and then we would have. Then it wouldn't be that time to estimate, to get the answer. Okay, so let's bring the L summation outside. And inside we get standard normalized Gaussians, 1 over q to the d, s mod q. And then we would have something like e to the 2 pi I, a s squared minus s dot L over q. So this is a standard Gaussian times Sorry, yeah. Yes. So now if we want to estimate this, so in absolute value, so for the standard Gaussian, you have a square root cancellation, that's very basic. You just take the square, expand it, and then you get this geometric series. So this sum is bounded by q to the minus d half, and that's the kind of q to the minus d half I mentioned heuristically before. So and in ZD, and maybe we remember the absolute value, the estimate we had for the absolute value of this term. And the estimate we had for the continuous Fourier transform, which unfortunately
It's up there on the top.
is it on the top?
No, not the estimate, but the formula for it.
Yeah, the formula.
Right.
Unfortunately, not on the top. But as we remember, so what was the Fourier transform? It was e to the minus 5 over 2 epsilon absolute value. Maybe I write it down to epsilon minus I tau. Remember, this is this tau. You say over 2 plus tau, so this is a small number times the square of this c minus l over q, which I will put the yeah. The absolute value of that. Okay.
Wait. Sorry for the inter. So we are estimating the whole double sum here?
Yeah, because this is the Fourier transform. The whole double sum is the Fourier transform.
And how do we do that? So
and then this is a formula. So you have to the absolute value, change the summation.
I
so
just do that.
Absolute value inside. This is q to the minus d half, and then you use the absolute value for just a continuous Fourier transform.
Because this can be pulled out from the inner sum.
Yeah, I mean, this is,
right.
You can just change the summation first. So you would have a sum in L, and then you put these two terms together and sum in S, because this depends on S, then you get this Gaussian sum.
But the G doesn't depend on S. That's the point.
G doesn't, yeah.
Right, so that's why we can...
Yes,
okay.
that doesn't depend on S, that's important. So what depends on, yeah.
Right.
So once you, this S in the Fourier space just gives you this vector. That's all what it is, because it's a shift and space you just multiply. So instead of doing this, you calculate the real part of that multiplying with its conjugate, what you get is an epsilon times epsilon squared plus tau squared. Yeah. And maybe I put the q here, the q squared here, so I do one more. Okay, so let's estimate this stuff. So the way we set up our parameters, the point is that this will be bigger than a constant, and then it will be very easy to estimate. So as a note, so how to estimate this? Maybe I can just see it. So let's observe the following. So what were our parameters? So we would have this P was A over Q plus tau, and this was in the fairy arc, kind of centered at A over Q. So then tau was less than equal than 1 over lambda times Q. So then Q squared tau squared is less than equal to 1 over lambda squared, which is epsilon squared. So if I write this instead of this, I pull the q squared out, and I have qc minus tau squared. Then this term, epsilon over tau squared q squared, is bigger than equal than 1. because q squared tau squared is less than equal than, oh, sorry, epsilon was 1 over lambda squared, so this term is bigger than equal to 1. But the other term is also, if I look at epsilon squared q squared, remember that q was less than equal than lambda, so epsilon squared lambda squared, and lambda squared is less than equal than 1 over epsilon. So this is also less than equal to epsilon. So if I put these together, then we get epsilon over epsilon squared plus tau squared q squared is bigger than at least half. So what does this mean? It means that you can forget to estimate this whole term, just replace it with a constant. And then if you sum this over all integers, clearly bounded by a constant, because you sum over integer points imagined in one dimension, this is just smaller even than a geometric series. And you sum because you have a square here, there may be one big term. So this whole thing would be bounded by q to the minus b half. Oh, I forget one thing here. Here there was this normalizing factor, this epsilon. Remember, epsilon was tau to the minus b half, coming from the Gaussian. Because when you take the Gaussian z x squared, you have a z to the minus b half from the normalizing. That's what we had in the continuousness. So if I put all this together, then I get the estimate. All the way down to here. So from the Gaussian cancellation, I get a q to the minus b half. From the normalizing factor in the continuous Gaussian, I get this epsilon plus tau to the minus b half. And the big exponential sum is just bounded by a constant. Because this is bigger than a constant, and then you just sum basically to the minus absolute value of L squared over the lattice points, which is clearly bounded. So we get this as long as again, and now what we have to do, we have to integrate this on all these intervals and sum up for A and Q and see that would be bounded, which is kind of easy to see. So then the integral, maybe I write 0 to 1. Oh, this is uniform in C. Notice that the right hand side does not depend on C. And where does C vanish? C vanished in this estimate, no matter what is C, doesn't matter because there is only maybe one term here where this is small. That's just a constant, that's just less than equal than 1. And then for all the other lattice points, at least one away from this point. And doesn't matter which point you do, this is a uniform estimate. So this is an infinity bound. And then basically it just less than equal, and then gives some u up to lambda, but it won't matter. You can sum now up to infinity because it will be, and then you would integrate. And what is the range of tau? Tau is less than equal than 1 over lambda cube, but that again won't matter. You can integrate to infinity. And actually, that is what is happening when you calculate the number of lattice points. That is, you take C equals 0. You extend these summations to get a nice asymptotic formula for the number of lattice points in the circle method. But to be precise, our range would be this. And then you will just have this q to the minus b half, epsilon plus tau to the minus d half. And then if you integrate this, again when d half is bigger than 1, then basically this is coming from the range when tau is going from 0 to epsilon, and that gives you an epsilon times epsilon to the minus d half. The rest is so that's the main contribution. So, and then basically that gives you epsilon to the minus d half plus 1 times the sum in Q, and I forget you also have numerators AQ equal 1, but for every Q you have at most Q numerators, so this is less than equal epsilon to the minus d half plus 1, sum in Q, and I said we can just extend the summation Q to the minus d half plus 1. So when d is at this v, this is convergent because it's at Q to the minus d half, so less than equal epsilon to the minus d half plus 1, which is lambda to the d minus 2, because epsilon lambda to the. And that's exactly what we wanted to show. All right, so that is the L2. Now, from this you get very quickly the LT when t is bigger than d over d minus 2, because you just do an interpolation instead of taking the infinity norm here. If you use Minkowski, so maybe I give you. Oh, I'm over already. I'm sorry. So I will continue as a homework. Modify this argument to prove the LP dialectically. Because basically, as a note here, what you have, if you take this A star F LP, that's less than equal than the integral of F star GT epsilon LP, again by Minkowski. And here you can do an interpolation. We already have the L2 for every t. And the L1 is trivial. And you just interpolate between the two. And then you get a convergent integral and exactly when p is bigger than d over d minus 2. Okay, so the LP.
So what's the L1 norm of, so you are saying the L1 norm of F and G. So what's the L1 norm of G?
Norm of G, but this is, I don't want to solve your homework, but this is less than e to the minus a constant epsilon x squared. So the rest is x to 1 over x squared, 1 over epsilon, which is lambda squared. So it's lambda to the d, is the L1 norm of G. The epsilon, and you just interpolate with the lambda to the d, and that is. I mean, there is a lambda to the minus. There is this normalizing factor, so you take that into consideration. So this is so, but again, this is just kind of the structure of this type of estimate, and doesn't give the fine structure of the Fourier transform of sigma on the head. And so the next time, basically, or I use maximal functions, like if you just take one lambda. The key thing here will be, and in some other results I want to discuss, is if you take in the discrete case, so that sum of x squared equal lambda squared e to the minus infinite x of c. So you take the lattice points on a zero shaded lambda, and you take the Fourier transform of this set. This is a very typical exponential summing numbers. All these exponential sum has the property that heavily depend on the arithmetic properties of C, whether C can be close to some rational points of small denominator. And that is the kind of phenomenon which is the analog of the stationary pacing, that in the continuous case, the Fourier transform is concentrated near 0. So if one wants to prove some analogs in the discrete case, not just the spherical maxima, but I will show you some other theorems, like another theorem of Bernini about large distances between points of a set of positive dense Euclidean cases. If you want to prove something like that in the discrete case, then one really has to understand the fine behavior of the Fourier transform, and that will be needed also to extend that is our newer proof of the L2 discrete spherical maximal theorem is to exploit basically a little bit not just uniform, but estimates which are sensitive to the properties of C. So that would be one thing I would want to talk about next time, to extend the L2. And kind of it's a funny thing, with this new approach, we couldn't prove the full LP discrete maximal function. Our old approach was more complicated, it was not some asymptotic expansion of the Fourier transform. So that's an interesting question. If anybody would be interested in how to prove LP with this approach. And then and after that, I wanted to discuss some other topics than the maximal functions. Some distribution results and some results in Ramsey-Touch results. So I'm sorry for taking a little bit more time. I will watch the clock a little more carefully next time.
Yes, thank you very much, Ákos. Is there questions or remarks?
So next time you are going to put together, because right now we just have an L2 estimate between lambda and 2 lambda.
Yes.
So next time you are going to put it together with some kind of interpolation for the full range, for the full range.
Yeah. Next time, basically when you take the superoverall lambdas, and then some other topics like some kind of equidistribution results of the lattice points on spheres in different senses. If you use the maximal function, you can prove certain ergodic, pointwise ergodic theorem. Averages over the solution set. So we will see. But technically it will work.
So, okay, so let's start here with this make everything 10.